Steve, take it away.
Thanks, Ingrid. Appreciate it. I will share my screen and then I'll probably turn my camera off in just a minute. So once I get started here, screen 2, there we go. All right. Thanks for having me. Much appreciated. So Steve Waalkes, I am the Executive Director and CEO of the Michigan Concrete Association. Assumed that role just over a year ago, but I've been with MCA for 19 years now, and actually been in the concrete and concrete paving world for over 25 years. So licensed PE in Illinois, master's degree from the University of Texas at Austin. That's where I studied concrete pavements in detail, in particular life cycle cost analysis of concrete pavements. Originally from Michigan, though, I was in Texas for 2 years for master's, worked in Chicago for 6 years, and then back to Michigan. So, but I am excited to talk to you about just the basics of concrete pavements today. And we got about an hour here, and we'll just jump right into it. We're going to cover really not in depth. It's a high level overview today of concrete pavements, the materials, some specific things to concrete that are obviously different than other pavement types. Obviously, probably being compared to asphalt, the thickness design is different. It obviously is a different mix, but we have to joint concrete pavements and little differences in base, subbase, subgrade support conditions underneath the pavement type. So we'll talk about again, basics of constructing concrete pavements and real quickly on maintenance and repair. So this is just hitting the highlights, but we'd be happy to entertain any questions as those come up. So feel free to ask those in the chat or the Q&A, and we'll pause and address them when we can. So real quickly, concrete pavements, specific things to concrete pavements that are probably different than asphalt. Some of the terminology, we talk about dowel bars, for example, if needed for load transfer at transverse joints, tie bars to tie lanes together or slabs together across longitudinal joints. The difference in those obviously being that the direction of travel is parallel to the longitudinal joint, and then you cross transverse joints as you're traveling in that vehicle, whatever the loading situation and whatever the traffic types are that are using this pavement. We apply surface texture to concrete because we can. Other pavement types you can't, but it's a fresh, liquid material before it sets, and so we are able to apply a surface texture to it to give it some skid resistance. And we try to pave it as smooth as possible for ride quality purposes, not from a surface texture standpoint. But we'll get into a little bit basic on thickness design and concrete materials as well here as we go along. So let's dive into that. First off, my personal pet peeve, and a lot of other engineers and some of you maybe on the call as well, is and we have some dear members of our association that we're funded by the industry essentially. And some of our dear members that are cement companies or cement construction companies, when you look at our membership directory, and you don't build anything out of this gray powders alone. That gray powder is the magic ingredient that makes concrete. It is what it is. And the analogy I like to use for those who, like the SAT type of analogies, that concrete is to cement as flour is to the cake. So the flour comprises the powdered, ingredient in that cake and makes it what it is. But you don't want to eat flour. You want to eat cake. So we want to build things out of concrete. We don't want to build things out of just cement. So please call it concrete unless it's just the gray, dry powder that is going into it. Let's real quickly on Portland cement. Why is it called Portland cement? Is that Portland, Michigan? Is that Portland, Oregon? Is it Portland, Maine? No, is the answer to all those. All those cities were actually named after Portland, England. And the cement is named after Portland, England as well, because the inventor of this, an English mason who experimented with this mixture of limestone, iron, silica, and alumina, primarily limestone, and patented the product that he made in 1824. The patent for it was called Portland cement because the finished product, when mixed with water, to create this magical binding agent. Resembled limestone that was quarried from the Isle of Portland in the English Channel, which is right near whereby this guy Joseph Aspdin was located in England. So it's since now Microsoft Word and other your Outlook emails, they'll try to capitalize the P in Portland, but most of the industry has stopped capitalizing the P in Portland cement if you're going to call it Portland cement. But the other word on this slide that's of note is that it's hydraulic, in that it's activated by just mixing it with water. And that a chemical reaction occurs. That chemical reaction is called hydration. You want to stay hydrated. Your body does, as well as concrete. Once the cement has had access to water, you want to keep that water because it fuels that chemical reaction if you put it at the right amount of water. And we'll talk about that in a minute. But that chemical reaction occurs, but it goes dormant for a bit. And so you can actually measure this with temperature devices when you mix water and Portland cement, or mix a batch of concrete together. It actually spikes real quickly in temperature, but then goes dormant, which is great for us because our construction practices have kind of evolved around that, is that we can mix it at a plant and then put it in a truck, or mix it in a truck if it's dry batch into ready mix trucks, and then we can haul it to the job site as long as that plant is located within a close enough range where we're still within that dormancy phase, like you see on this slide, that kind of teal blue color. Typically last anywhere from 2 to 4 hours. You can have special admixtures that extend that out to 8 hours or more without negative effects. But then that chemical reaction will eventually kick off, and it gives off heat. It's an exothermic chemical reaction. This is not a chemical engineering seminar at all, but that's about as much as we're going to get into it. The water and the cement powder chemically combine, give off heat in that process. They chemically combine, and then the grains of cement actually react with that water and grow crystals towards each other and lock everything together. That's the product of that reaction, are these crystals. So that's what's happening when concrete actually gains strength. Eventually, the reaction stops and it goes down in temperature, and there's things we have to do to the concrete at various stages because of that. So we'll come to some of those things in a minute. We don't just do cement and water to make concrete. That's just paste. We add a bunch of filler to it to make it better, to make it shrink less, to make it more stable. And so we add aggregates of fine size, small size, that's we call sand, and then larger size we call coarse aggregate. Sometimes we might have an intermediate aggregate, which is technically still in the coarse range. Other cementitious materials, not just Portland cement, such as fly ash, slag cement, or silica fume, or other new products being researched all the time, as well as chemical admixtures. Here's a shot of that reaction, that an artist's rendering, I guess you could say. The gray cement particle in the middle, the black hairs that are growing out are the start of those crystals being formed, and the blue is the water. And you can see neighboring cement grains also growing those crystals, and there's still some water in between, so they're not fully locked in yet. But the whole point is to have these crystals grow to each other and fully lock in. So with adequate amounts of water, theoretically, the concrete or the cement would need a water cement ratio of about 0.25, but that is not a workable concrete mixture. So we typically see water cement ratios higher than that, up to usually 0.45, maybe 0.5 max, and usually in the 0.4 to 0.45 range to have adequate workability and constructability, but also then minimal shrinkage and adequate strength. Because all that extra water is good for workability and things like that, but too much will start lowering the strength, increasing the permeability, reducing freeze thaw, more cracking, and lower bond strength. Then lower strength in general would result in lower bond strength in reinforced concrete structures. Also allows settlement segregation, which is kind of an example of what we're showing in this sample here. That all the coarse aggregate is near the bottom, and all the fines and fine material, fine cement particles, and just higher paste volume up at the top in this sample here. Aggregates in general, this is kind of from a theoretical perspective, what we want to do when folks design concrete mixtures, proportion those concrete mixtures. They want to shoot for the most amount of aggregate that you can pack into a known volume. So you want aggregate of all sizes represented. You want as big of an aggregate as you can allow for the member that you're placing. There's ACI guidelines on that. 1/3 the thickness, no more than 1.25 times your smallest bar spacing. But if it's a reinforced concrete structure, there's lots of different things that to determine that maximum aggregate size. But given that, you want to have aggregates of all sizes represented. So there's kind of an art and a science to that, but that results in the best mix as far as from a performance perspective, strength and shrinkage, but also the most economical, because the cement powder is actually the most costly thing in the concrete. So what makes it concrete? Cement. You can't have concrete without cement, but you want to minimize it for cost as well as for carbon reasons. So real quickly on chemical admixtures, there's 4 main types with exterior concrete in freeze-thaw environments, which is pretty much everyone on this call, except maybe in Arizona. Southern Arizona, you don't generally need air entrainment for freeze thaw. You probably do in the northern and mountainous parts of the state, but and same thing with Florida. Southern Florida generally doesn't use it for freeze thaw. They may do it for reduced density reasons, reduced weight in a structure, for example, perhaps, just to try to reduce that density and reduce the weight on that structure, but occupy the same amount of volume. But regardless, the freeze thaw, the main thing you get to achieve freeze thaw resistance is having air entrainment on a microscopic basis. So air entrainment admixtures are surfactants, which means that they act just like soaps do in the presence of water. Liquid soap in the presence of water, when agitated, creates foam, creates air bubbles, and distributed throughout the cement paste, that gives us freeze thaw resistance. They act as little pressure relief valves, like shown in the photo there. Other common admixture types are water reducers, accelerators, and set retarders as well. So we can speed up with chemicals, we can slow it down with chemicals. Are set depending on what we need for the time of year, cold, hot weather, whatever it is. And water reducers in general allow us to get higher strengths, yet still maintaining workability and slump without the use of water. So you can still have that lower water cement ratio, lower shrinkage, higher strengths, higher early strengths, etc., but you achieve that through the use of chemicals. So that's pretty
We've
much
got a
it as far as,
question,
yes,
Steve.
let's
Sorry, we got a
pause.
question. Is there an issue with having too much air? Can you have too much of a good thing?
Yes. What happens is above normal specifications are around 5 to 8 or 5.5 to 8.5, or depending on where you are and what specifications you're working under. That's the normal range of when we measure it by volume using typically a pressure meter or alternatively a rollometer to determine that air content of the fresh concrete. So any percent above that range, typically, or above what we designed for, every additional percent of air reduces the strength, because there's no strength in air. There's strength in cement and aggregates and everything else. So if we're putting more air into that same volume of material, it reduces the strength approximately 8% for every 1% above the range. So yes, it'll start lowering the strength, but typically where strengths are generally not an issue for most pavements and even for most structures. There's definitely a factor of safety for the design, and then also in the specification and the mix design to achieve that specification. So there's typically factors of safety involved. If you do get high air, it's generally not a main concern. Once it gets much higher than 10%, you start seeing permeability issues, which then could potentially lead to some freeze thaw issues. But yes, you could potentially have too much air. Most specifications obviously limit that, but high air is generally better than low air when it comes to durability, and that's the main reason we put it in. So good question. On pavement design, let's get into specific for pavements. We talked about the material real quickly. Again, this is not a pavement design course. I just want everybody to understand all design procedures pretty much take all these engineering things into account. As most engineers understand, we design things to reduce the stress on that member, on that material, whatever it is. And so that's one thing we can look at is what stress is being induced into this slab, in this case, slab on grade, fully supported. It's not a, cantilevered beam or all these other design situations you may have learned if you had statics or dynamics or, these other design courses. Concrete's very strong in compression and relatively weaker in tension, like we see on this theorized stress diagram here. Compression in the top of the member and tension in the bottom once under load. Obviously, a slab on grade is not seeing the same thing as a beam or a slab that's supported on the ends. But that tension still is the critical design. And when in concrete, we measure it with flexural strength, where we actually break a beam, a simply supported beam that's supported on the ends to determine that number. But it's a 1 degree different in the entire, there's an extra 0 on the compressive strength, right? It's 10 times, roughly 10 times more stronger in compression than it is in flexural or tension. So that's our critical stress. We got to design for that. But even if we don't exceed the strength of the material with that stress, over time, repeated loadings could lead to the fatigue principle of where if we're roughly between 50 to 90% of our strength with that ideal stress or maximum stress condition, it will eventually add up to the point where repeated loadings will cause a fatigue crack. So that's really what the main principle is that we're designing for on the stress side, the engineering stress side. I have one more after this. And a question?
Yeah, we got a question about, is there a concern with cement content? So this person says they see suppliers really adding a lot of cement to ensure early strength gains, even if they're specifying a specific mix, the M.P1 mix. They're seeing folks putting in extra cement. And is there a concern with that?
Yeah, good question. Most specifications will limit that, the maximum cement content for various reasons. But the concerns with having too much, I understand why. The contractor wants early strengths. It doesn't matter what the final or ultimate or 28-day strengths are, but they want to be able to pull the forms or build the next phase or whatever it is, use the thing that they're building for the next operation. That's why they're doing it. So, but the concerns with too much cement, yes, more cement means more shrinkage, and generally more cement, especially once you get above probably 6.5, 7 sac, means reduced durability with most mixes that we see. And then you have with more shrinkage, more opportunity for extra cracking, uncontrolled cracking that you didn't anticipate for. So, and also increases the cost. So, not recommended. It's good to have a reasonable upper limit on that cement content. Even if we don't, again, have those loads over time with multiple repeated loads, we could get that fatigue crack to occur, even if we've never exceeded the strength. The other engineering principle we look at is deflection. Again, it's fully supported slabs on grade. We don't get a lot of deflection like we would with unsupported slabs or simply supported on the ends. But that deflection still, we account for that in the design procedure. All design procedures are calibrated, or at least look at that in some way, shape, form, or the other. But if we could limit that deflection, we'll get better performance out of the pavement. And so a better support underneath the slab or a better load transfer between slabs will allow for a better, more efficient pavement design. Even if we limit those deflections to a smaller amount, but that still is occurring, that could potentially cause erosion or pumping of the material underneath it, if that is susceptible to it. Because what happens is that load occurs, the material, if in saturated condition, especially springtime, spring thaw, is our kind of our critical time of year, can allow that material to be pumped and churn underneath that load and move around underneath if we do have high deflection. So we want to limit that with better bases that don't have a high fine content in them, as well as, if needed with heavy loads, having some sort of a load transfer between slabs. So that could result in faulting long-term, rough pavements, and potentially cracking if there are heavy loads in those low support conditions. So all pavement design procedures and things to think about as a pavement designer is, do we need load transfer? given our situation, given our support conditions and our loads. And the main thing of how thick do I need to build this slab? We help with that at our association to all specifying agencies and their consultants. We offer that design assistance, answer questions, guide people to the right things, resources and such to help with that. But the main things you need in order to determine how thick does my concrete need to be is what's going to be on top of it and what is underneath it. Those are the two things. And then once we know what's going to drive over top of it and what it's sitting on and over how much life, how long do you want it to last, then we can determine how thick, how strong, and the details of load transfer and things like that. But if you have more trucks, you need more pavement. It's regardless of what pavement type it is, concrete or asphalt, that's definitely the case. But that is the determining factor. What do we typically see for Michigan road and street designs? Anywhere, these are, what could be built. I know it's not always, well, we build, 7-inch residential subdivisions here in our Metro Detroit suburb that we work in, understood. Or we always build 8-inch arterials, or we always build 9-inch industrial roads, or whatever those numbers, understood. Everybody has what's worked well for them if you have, but if you've not built one or are starting from scratch or, want to check your designs, these are typical ranges of what we see for thicknesses for the different classifications of roadways, and the different support values or ag bases and on a truck traffic you can drive on. So in general, the rule of thumb that we tell folks is if you have a concrete slab, if you add an inch, you can almost double the traffic load carrying capacity of it, whether it's the weight of the vehicles, the number of axles that are driving over 20 years, however you want to characterize it. It's a good rule of thumb. So my 4-inch driveway, residential driveway, can only probably handle one truck a day, at most driving over it. But if you can go to 5 inches, you can go to, 3 or 5 trucks a day, maybe. And if you can go to 6 inches, you can go to, 10 or 20 trucks a day. So that's good. That's a good rule of thumb. Every inch of concrete adds a significant amount of load carrying capacity. And with parking lots, similar thing. It's a lot of parking lots, the loads are distributed differently. Obviously, in a highway, in a street road, they're confined to lanes, and they're repeated loads over and over in those the wheel tracks of those lanes, the wheel paths. In a parking lot, they're distributed over a larger area, so you can generally get by with slightly thinner sections, except in those true drive lane areas where they're concentrated. And then there are resources for those. Both pavement types, we get that all the time. What's a quick way of determining how thick it needs to be? ACPA has a good website, pavementdesigner.org. Check it out, bookmark that, go to that in the future. We can do future webinars on just pavement design, or I can teach that to folks. So just note that and look at that for the future. We'll gloss over it for now. What about curb and gutter? This is one of the MDOT standard details, as shown. F curb with gutter, then the width of the gutter pan, depending on which detail you choose, and then the number of that detail, depending on the width, and then if it's adjacent to asphalt or concrete. So no lane ties if you're adjacent to asphalt, and so those are the even numbers that would be specified, and then if it's tied to concrete, would be the odd numbers, and then the joints would have to match the joints in the slab. But just real quickly on curb and gutter, and then on that lane tie spacing, we get that a lot. That is on one of the MDOT standard plans as well. R41, I believe, is the number that this is taken from. Yeah, it's based on how much concrete width is being tied together. So that's how I'll explain that right now. But again, we can go into detail on that in the future. Joint design, where this is kind of all going into here. I could teach a whole 1-hour webinar on joint design. Just know that obviously it's different than asphalt. We have to plan for joints or regular intervals in the concrete because of the natural concrete shrinkage that occurs. And so a well planned out spacing, depth, location, etc. of these joints will help control that cracking and result in a good looking slab. We've gotten away from using wire mesh in concrete in our state. Thankfully, I still see it used occasionally, but it generally interferes with the working of those joints. So it's not recommended to be used by us or by most folks. And if you want to debate that, we can take that offline and talk about that later. But to be used effectively with a good joint spacing to control cracking and not have any cracks, it actually ends up being worthless. So because each piece of wire mesh, each layer of wire or piece of wire mesh, I guess, has to be sized such that it's smaller than the slab that it's in, the joint spacing. So if you have 10-foot by 10-foot squares, your wire mesh should be cut to 9 by 9s or 9.5 by 9.5 foot max pieces of wire mesh embedded strictly within each slab and not going across the joints, because it actually will interfere with the working of those joints and can potentially cause cracking away from the joints, when that's the whole purpose of the joints, is to control the cracking. So if you're gonna plan and want to have cracks, then use wire mesh. If you want to have a crack-free pavement, don't use wire mesh. That's really what it comes down to. Ingrid?
Yeah, we got a question. Other than airports, are there any places where the specs significantly change from the typical specs because of traffic loads or weight of trucks or weight of traffic or amount of traffic?
Yep, very good question. Every type of facility will have probably different specs. So yes, airports, if it's a commercial airport, it'll be FAA. If you decide to do some at a general aviation airport with aircraft traffic under 60,000 pound gross aircraft weights, you're allowed to use highway specs. So then you can use FAA, but you could use MDOT specs then. Again, MDOT would govern any federal aid stuff, even built at the city or county level, typically, unless they choose to use some special provisions or other which are approved. But then at the city and county level, non-federal funds, they can use their own specs. And then commercial places, you'll see a lot of reference to ACI specifications, and ACI has guides on concrete parking lots and concrete pavements. So it really depends. Yeah, it all depends on the facility that you're using, and the load, the thickness of the slabs will depend on the loads using that facility. I've seen MDOT thicknesses are usually in the, well, they do some 6-inch concrete overlays, but they'll go up to probably 13.5 inches is probably the max I've seen on MDOT highways, interstate heavy duty, like I-75 type. But I've seen some private facilities with heavy duty manufacturing and unique loading situations with heavy duty non-pneumatic tires, foam filled rubber or hard rubber tires where 14, 15, 16 inches are needed. I've seen FAA facilities, most recently a DTW, do 21 inches, 21 inches of concrete, I believe. So yeah, it all depends on what's driving on it and what it's supported by. So good question. So we put joints in concrete. I alluded to this because we have to. It's going to crack otherwise, and the cracks because of various reasons. Primarily drying shrinkage. There's extra water in there than we actually need chemically to hydrate the cement. It also, that temperature curve I showed, it'll contract thermally, and that reduction in temperature from the peak is cause thermal contraction. And then there are curling and warping, which is difference in temperature or moisture from the bottom to the top of the slab. That can induce some stresses, which might cause cracking. So that's the whole reason why we joint and why we joint at the typical spacing that is recommended, that I will get into very quickly. The types of joints that you will need to account for: isolation and expansion joints have some compressible material. It is, as noted by that kind of thicker line shown on the left. Contraction joints or control joints are ones that we either tool or saw cut into the top in order to, again, purposely control the cracking, and we want a crack to occur. So I like to tell people concrete is going to crack, and the joints are just straight cracks that we planned for them to be at that location. And then a crack is also a joint. It's just an unplanned joint location which sometimes is is a little bit of objectionable to a lot of owners. But so that's why we want to make sure that we plan the locations properly. And then construction joints are the edges or end of our pour, or denote one pour to the next typically. And so that's more of a up and down straight formed type of joint typically. You could, like I said, saw or tool the joint. Usually transverse joints are 1/4 of the thickness, and longitudinal joints are 1/3, because there's typically lane ties, deformed bars underneath that longitudinal joint in many cases. Having a little more restraints, you go a little deeper to make sure it occurs there. And then you can use early entry saws, or sometimes called green saws, or name brand is soft cut saws. A lot of them are called that, to get on the earlier in the window. And I'll talk about that real quickly. That's that early part of the sawing window where it's still gaining strength. The reaction is still occurring, hasn't stopped yet. But they're lighter weight saws, and they are have a shoe around the blade to hold the very, very green, very young concrete in place, and all the aggregates in place, so that the blade can cut through them and that doesn't rip them out as it's cutting. Otherwise, you wait longer and get on it with a heavier saw. That's a wet saw that creates a slurry. That's more of the conventional sawing window like we're talking there. All right, let's talk about how do we joint pavements. I'll just talk in general. I'm not going to go through an example again. This could be a whole talk just on this. You have to match existing joints or cracks from either old concrete or even just the previous placement next to it. The joints need to continue all the way across the width of the concrete that's being placed, or the length of concrete that's being done, all the way to the free edges. Place joints to meet in pavement structures. What we mean by that is, in parking lot, light pole bases that the electricians, conduit, and then they sonotube, and then they put those in, and then we come in and pave. And then if we choose to use concrete, line up joints with those. In a warehouse floor situation, big warehouse, you have columns spaced throughout there. Joints should always intersect those columns, both directions. Manholes in an exterior roadway or parking lot situation. Manhole or drainage inlet or some sort of structure that goes many, many feet down and doesn't move, but think of the pavement as being able to move, and you need it to account for that movement away or near that structure. So that's what I mean by in pavement structures. Remember, your maximum joint spacing is based on thickness when you do plan out your joints. It's easiest to place joints where pavement changes slope, whether it's a peak, a crown, we like to call it, or a valley, or the bottom, the flow line maybe to a drainage inlet. It's easiest constructability wise to make that change in slope a joint for the contractor to make that a formed joint usually, or if they have equipment that can do that break, they can plan for that. And then things you don't want to do when looking at joints. Any dimension of a slab less than 1 foot, because it's hard to get a saw blade down and create an adequate depth of a cut if it doesn't have at least 1 foot distance of joint to be cutting. And then typically the general max is 15 foot. This is for most city, county, highway, as well as parking lot type paving of standard types. Granted, FAA has their own design guidelines for joint spacing. And it's based on the taxiway width or the runway width, and then to that maximum, but they'll divide it out equally. So we generally see a lot of 18.75 foot panel sizes at airports because of the runway or taxiway widths and the maximum thicknesses that they allow to control cracking. So avoid acute angles, anything less than 60 degrees. And you do this by dog-legging joints through the curve radius, and avoid L-shaped slabs, interior corners, or re-entrant corners, some people like to call them. And we try to avoid odd shapes if possible, but it's virtually impossible. Again, referencing FAA, they end up putting wire mesh in each individual odd-shaped slab. Again, they do reinforce and do mash or rebar in some of those, but they don't extend it across the joints. Question?
Yes. So we got somebody who's saying that Ohio ODOT is utilizing epoxy coated contraction baskets on their mainline paving, and they're wondering if you know of any plans for Michigan to do the same.
Michigan MDOT has researched that in about a decade ago or so, and they decided to go to the purple epoxy on the dowels themselves. They do not require the basket assembly that the dowels are tack welded into to be epoxy coated. So that is still plain black steel. But the dowels themselves are now the purple epoxy, not the green epoxy. Green epoxy is great for rebar. It's bendable and it stretches. And so you can field bend rebar if it has that green epoxy on it. The purple epoxy that they switched to with the dowels is a more durable epoxy. It's more rigid. It's not bendable, but you don't want dowels bent. You want them perfectly straight and aligned in the joint. And MDOT does use them for almost all their paving at all transverse joints, in the lanes at least, not usually in the shoulders. But the basket themselves that those dowels are tack welded into to hold them in place during the paving operation, those baskets are still the plain black regular steel.
Gotcha. Then there's another question of, would it be appropriate to add a joint on or before culverts?
It's probably, I will tell you this, I've seen a lot of drive approaches, whether it's commercial, but in a ditch situation where then there's a culvert going underneath the drive, where if they do not, depending on the amount of aggregate base material in between the bottom of the slab and that culvert and the culvert type, plastic, metal, or concrete, in general, I'd say yes, especially in those rural situations where you have that. I would probably try to plan for a joint, technically a transverse joint going across that drive approach that lines up right over top of the center line of that culvert. Because I have seen it where we have, whether it's some heaving or settlement or differential support or whatever it is, it's probably a good idea to do that over top of that culvert in those situations. For the like 3-sided or 4-sided concrete precast box culverts, generally they have adequate amount of ag base over top of them. They're usually not, being used as a bridge deck over top. Although in low clearance situations, maybe they would be, or some unique situations. But in those, generally is not necessary. The joints don't have to line up over top of a box culvert. Good question. Getting into those maximum joint spacings like we talked about, in general, we recommend 2 times the thickness when going from inches to feet. So on a 4-inch sidewalk, your max is 8x8 slabs. It's best to be smaller. That's why 4-inch sidewalks, if they're 5-foot regular sidewalks, we usually go 5-foot by 5-foot squares, typically works great. If you're doing a 4-inch pathway trail, for example, Jackson County's done a lot of concrete trails and pathways recently, 8-10 foot. If they go 4 inches, they could probably do the 8-footers with 8x8s. But if it's a 10-foot wide and they want to keep at the 4-inch thickness, you probably have to go 2 5-foot slabs and do 5 foots to do that concrete trail or path or multi-use path, whatever you want to call it. And so we've seen some agencies, just switch to 5-inch and then do the full 10-foot by 10s if it's a 10-foot pathway. But regardless, that's kind of the max that we'd recommend. Smaller is always better, like we said, and you can make adjustments if needed. And kind of 15-foot for normal situations, like we said, is your absolute max. About on sidewalks, I mentioned that 6-inch sidewalks. We've seen some where, especially in areas where they're going to have some heavier snow maintenance equipment. If it's not just going to be a small little pickup, or it may have a pickup with a salt spreader on the back, so it may have some heavier weights. But they're worried about a 4-inch sidewalk and having snow equipment being at the heaviest loading situation. They might bump it up to 5 or 6 inches, and then you can do your full 10-foot by 10-foot slabs. What about curb and gutter? Well, if you're doing it next to asphalt, number one, it doesn't have that lane tie in it. As we saw in that diagram earlier, the M.F curb detail. Typically, those are done at a 10-foot roughly spacing. A lot of times the crews will tool them in instead of saw cut them in, because saw cutting requires a separate operation to drop back a little bit later. And they prefer to the finishers just do it while they're there. Problem is with that, sometimes they don't tool it deep enough to actually force the concrete to crack at those locations. So look at that. And then if you are doing concrete, is in this case, you see this is probably a roundabout. I think, yeah, this is a roundabout approach. You can see on the background of that photo, and they've already formed the inner ring of the roundabout. This I think was a full concrete roundabout. The problem with doing the curb first is you have to know where if you're going to tie it, especially, but even if not, it's going to have some friction or against each other, some keying into each other potentially. You're going to have to know where the joints and the slabs are if you pour the curb first, so that they can match the curb and gutter. So you have to have that joint detail done and know that it's not just going to be at the regular 10-foot spacing. Joints in the curb have to match the joints in the concrete pavement adjacent to it. So that's why I like to see the slab done first, and then we just put the back of curb form in there, and then, or if you can machine do it, but for jointing reasons and controlling of cracking. So the other option would be is if you choose to do the curb first and then do the concrete pavement adjacent to it, then you could use a flexible expansion material. I like the 1/2 inch closed cell foam, I believe it is, flexible foam to go around curves and things like that. That can be done on the front of that gutter pan if there's concrete pavement adjacent to it, or the back of the curb if there's concrete sidewalk adjacent to it. I like the closed cell foam the best because it doesn't hold water like the asphalt fiberboard or the open cell foam does. Okay, now let's get into building the thing out of concrete. There are options for subgrade treatments. We don't see a ton of this in Michigan. We're seeing some agencies or some owner types use it for certain areas where we have some poor soils. As far as chemical stabilization of the clay or silty soil or whatever it is, whether using lime, fly ash, or cement, there are options to stabilize those soils. Whether it's applied in a dry powder or a slurry, and then pulverizer, mixer, reclaimer comes in and mixes that in, and then it's compacted. There are options for that, but in general, standard subgrade treatments are typically done, or if you're in a sandy soil, that's good to go typically as your native subgrade. And then subbase types, concrete will work on anything pretty much. It's just a matter of the details as far as is it going to bond to it? Is it a bound material? Do we need a bond breaker? Those things. There are agencies that like asphalt bases for their concrete pavements. Illinois Turnpike Authority is one of them. And I know in Texas they do lime stabilization of the soil, and then they just put asphalt directly on the lime stabilized clay, and then they do concrete on top of that. They don't use an unbound aggregate, base layer in between. In Michigan, typically, if we're on a clay or silty soil, we probably will do a sand sub base over top of that, and then an ag base over top of that, and then our pavement, asphalt or concrete on top of that. With concrete, we generally don't need as thick or as many, sub base layers. It's more of constructability than it is support for the pavement. And so if you have a very loose or bad subgrade material, just for constructability reasons, it will benefit the pavement long-term performance, but really it's more of let's get out of the mud so that these subsequent operations don't get stuck. But we don't need thick or super dense layers underneath our concrete. We just need it to be stable, uniform, and drainable. And then once the base is done, let's start placing concrete. Could place directly from the chute of the truck. This is a parking lot operation, but done on roadways all the time. Regardless of the pavement equipment being used to do the concrete, we've seen belt placers or conveyor belts, be used to get into areas, or if there are, areas where the base is just not suitable for getting trucks on that base material, because concrete will work on just a sand layer. It will work on an aggregate layer, or a looser aggregate layer. It will perform, but for constructability reasons, you might need some of these types of equipment potentially. You may need a pump. Obviously, in a lot of structural concrete is using pump floors and parking structures and things like that, like are pictured here, but sometimes used for pavements and flat work as well. Line pumps or boom pumps, depending. And then strike off equipment. There are a ton of options for strike off, but let's pause for a question.
Yes, so we got a question if there's a good minimum base thickness if you're using gravel for machine placement.
Okay. In general, an aggregate base or gravel base, I personally like to see some drainability to that material. Number one, as far as what material should we use? Do we use 22A, 23A, or should we go, MDOT uses a 4G drainable base. Personally, I like 21AA. It generally results in a material that's stable, but also drainable. You can also use crushed concrete as the 21AA material if you're in an urban area where you've got recycled concrete available. It locks in really nice and tight, yet still has some void structure to it. It doesn't hold water generally, usually, in most situations, and has some drainability to it. So as far as what gradation materials should we use and what should that constitute, what material should constitute that gradation? Again, 21AA. On the coarser side, I'd say probably if you could, and then whether it is natural gravel, crushed limestone, or recycled concrete, they all work well. Obviously, for MDOT work, they can't use crushed concrete within like 250 or 500 feet of a waterway because of potential calcium carbonate being as the water goes through crushed concrete, et cetera, et cetera. But anyways, those concerns, that's probably as far as thickness then, minimum 4 inches. And then probably once you get above 6 inches, you don't get any benefit in the concrete from the thickness design or from additional support offered or anything like that. Generally, I'd say 4 to 6 inches of 21AA of either gravel, crushed limestone, or recycled concrete. Those are what I would, in most situations, unless you've got some unique loading and heavy loads. The example you see with the conveyor belt and the 3D screed here against this reddish barn color building there in the top of this slide, that's just a sand base, I believe. They're just using sand in that case. That's just like a 6-inch parking lot for a light duty contractor, I believe. And just as a storage yard and parking lot. So, but as far as getting into strike off, it can be as simple as 2x4. You'll see that on, sidewalk jobs. They'll literally just have a 2x4 pulling along the forms, striking off the top. Could be an actual aluminum straight edge. That is essentially an aluminum 2x4 and typically holds its dimensions better when it gets wet and things like that. Whereas natural lumber can have a tendency to warp over time or whatever. Could use a roller screed, a vibrating screed that's pictured bottom right here, a vibrating screed or truss screed it's called sometimes. There are also vibrating screeds that are not truss screeds. Like you see being used bottom left here. Sometimes one of the brands is called a copperhead, I believe, but it requires the workers to obviously be in rubber boots because they're walking in the concrete as they're backing it up to strike off. A lot of times they'll pound in grade stakes in the placement area so that they know that the top of the stake is right at the level of the concrete, so that they're trying to get the thickness and the smoothness that they want at the right elevation there. But the laser screed pictured top right, that's a lot of parking lots, and obviously warehouse floors are done that way. And then slip form paver as well. We'll have some shots of that as well. But hand placement, like you see left side here, whether that's a lumber 2x4 or an aluminum strike off, I'm not quite sure. But that's, fairly typical. We see a colored concrete intersection being done. Hand work primarily, and then getting out there with the bull float and some hand floats along the edges. Roller screed, what do I mean by that? You see a single tube roller pictured on the left, triple tube roller on the right. The triple tube roller obviously heavier and has one of the rollers as a drive roller, whereas the single one just is going against the workers. It's trying to go away from them as they're backing up and pulling it manually with their labor, to pull it. And so those are two examples, both considered roller screeds. Obviously, the heavier one will probably result in slightly better ride quality, but again, is a much heavier piece of equipment to move around instead of two workers being able to lift it and get very mobile with just a single roller. The truss screed, vibrating truss screed in this case, it has an eccentric, motor vibrating the whole thing to get some consolidation at the surface. Doesn't go very deep, so you might need some internal vibration on that, but it strikes off as well. And again, as the workers have to pull it along Sometimes you'll see those still being used today. The VibraStrike or Copperhead on the left has some vibration to it. That's why it's got a motor mounted to it with an eccentric weight to give it some shake to it. And then the laser screed on the right does a great job of accurately screening off the surface of the concrete with a 3D profile fed into it, and can result in very, very accurate elevations for that concrete slab, floor, parking lot, or whatever it is. And then straight edging is typically done to cut off the tops of any bumps. So that's typically one of those 2x4s, but mounted on a handle. So the worker can do it from the side and not have to walk in the concrete to be striking it off. But this is after strike off. They're cutting off the tops of bumps and pushing it back and forth. And they're also then identifying areas and can see areas then of daylight underneath it, where they'll then signal a finisher to come with a shovel and throw some additional material to bring up any bird baths or low spots. So that's done after strike off to identify those areas. And then after that, a bull float, such as what we see pictured here, comes in to seal the surface. You make sure your bull float is straight and is in good condition. Typically, you do it flat as possible with maximum contact. You don't have it on an edge as you're pushing it across. Overlap, stop, and don't over float anything, which brings excess fines and water to the surface, which negatively can impact your surface. So it doesn't have to have the rounded edges. It could be a square or a rectangular shape like you see pictured here being used after the 3D laser screed. And then the one on the right, you can see that it has the rounded edges being used, but it's flat in nature, just to give it a seal up the surface. And then final texture is applied after that. So we'll get into that in a minute. Now, in regards to what do slip form pavers do, they're obviously a heavier, typically, piece of equipment. They're paving from left to right in this photo. The concrete's being deposited on the right-hand side of the photo. And that's the head of concrete in front of it that it kind of bulldozes and pushes. But there's typically an auger to spread it out, an initial strike off, and that strike off can often move up and down, actually, as a tamping kind of motion. Between that strike off and the tamper, which definitely does move in an up and down motion, is called the grout box, because that's where the vibrators are operating and liquefies the concrete. And then the concrete goes underneath that tamper and the mold behind it and is extruded out the back, and the side parts of that mold, the side forms as well. And then it relaxes to its final shape behind that. And when looking at a machine like that without any concrete on the showroom floor of a big trade show, you can see the auger on the right-hand side, that initial strike off, the array of vibrators in there, vibrating, consolidating the concrete, liquefying the concrete, even very dry 1-inch, slump type of concrete. When you look at it from on top, when you climb up on the machine when it's operating, it looks like gray water in that grout box area when those vibrators are working at typically 5,000 to 8,000 vibrations per minute. And then you see the tamper bar and the pan behind that, the mold, the underside of that kind of extrudes the slab out from beneath it. So slip-form paving is very similar to putting toothpaste on a toothbrush. The more you squeeze, the faster you have to go along your toothbrush, the harder you squeeze in order to have a consistent line of toothpaste on your toothbrush. If you just stay in one spot and squeeze and then jerk it really quick, there'll be a nice bump in there. So it's matching the speed to of the equipment to how hard it's quote unquote squeezing, which it doesn't literally squeeze, but it is being liquefied and then pushed out the back, or the machine is going over top of it essentially. But that's what's going on with slip form paving. Question?
We have quite a few questions, but we are close to the top of the hour. Steve, if you're willing to keep going, we'll keep going for sure. If any of you guys have to jump off, I did just put the link for you to get your certificate of attendance for today's session into the chat. Please use that. We are going to record the rest of this session as well. So if you do have to jump off, we'll send the recording out later so you won't miss out on anything. We have quite a few questions, but I'm going to let Steve kind of keep going for a little bit. We'll wrap up the content and then we'll go back and circle back to some of the questions. So
Okay.
Steve,
Sounds
keep
good.
on going.
Okay, I'm sorry. I tend to get long-winded. I love talking about this stuff.
That's all right. We got lots of questions too.
Okay.
So it's all good info. Keep
All
going.
right. As you can see, different molds, standard, rectangular paving molds, slip-form barrier wall, curb and gutter molds, lots of different options. It's a very unique one on the left there that I haven't seen very much. The one on the right, it's interesting to note that they actually, the edge of the pan actually tips up, and the side form usually has a bit of a batter to it as well to allow for a little bit of slump so that it comes out to a completely square edge. And a flat top and a vertical edge there. So it's all in the art of setting up these machines. After it extrudes it, applies a surface texture, initial surface texture to it with typically some burlap drag, and then some tining rakes. I'll see if I can in here. These are the tining rakes being pressed down onto the surface of the concrete, and as the machine drives along, puts those longitudinal grooves in there. MDOT switched in 2006 to longitudinal tining, and most others have followed if they have high-speed roadways. Lower speed roadways, we typically don't put the grooves in there. We'll go with a aggressive turf drag or a very much more aggressive broom texture. And then lower speed or pedestrian areas, we typically have a lighter broom texture. And then curing follows that. This bottom left has a shroud around the curing nozzles as they spray down onto the surface, as well as a nozzle onto the side. And you can see top right that being done. Top left is being done by hand, and then bottom right showing the white curing compound, which is kind of the standard for most agencies, because you can see the coverage. And then as an inspector, you want to see perfectly white painted white concrete. You don't want to, you wouldn't want to pay for blotchy curing. You'd want essentially think of it as a painting contractor. If they're spraying, your gray wall white, you want complete coverage. So real quickly, we're going to wrap up with maintenance and repair. The most common technique only, just so folks get an idea of it. We'll talk about full depth repairs. First off, terminology, your doweled joints in your repair area are CRG joints. We do not typically see a lot of TRG joints anymore. There's still a pay item for it. Not recommended to be used in most situations. So I have that X'd out here for those of you that are familiar with the MDOT items and maybe haven't seen these in the past. Your doweled, that's where you're replacing an existing expansion joint in concrete. You need to account for that expansion in the repair next to it. The repair area, in this case, being the one on the right-hand side that has the expansion cap going on it. This is back when we did reinforced repairs still. This is an old photo, so take the mesh out of here. The expansion caps are those silver bullets you see on the left. There's a gap inside the cap before you get to the bar, and expansion paper against the existing slab on the left there. The right-hand side has the CRG joints. You pay for that for a lineal foot of joint. So even though there's 10 bars on each side, you pay for, in this case, 12-foot lanes. You'd pay for 12 foot of CRG joint on the right and 12 foot of ERG joint on the left. That's a separate pay item. If you have a joint in the middle of a long repair, that would be paid as a CP joint, which is there's those baskets. This is an old photo, so it still has the green bar, and that first bar that we're looking at is actually pushed down, which is not good. But nowadays we'd see probably the purple baskets being used, and that has to line up with existing adjacent joints and cracks, especially if we tie them together. I don't like this one, number one, for the wire mesh. This is actually 131 from years ago, downtown Grand Rapids, those of you that are on the west side. And it shows those dowels installed and greased with the RC250 bond breaker material, but we're missing, that's an existing joint right there. We need to put a CP joint there and then probably not tie the red area of longitudinal joint. We could potentially drill and epoxy some tie bars in these green areas, potentially between the patch and the adjacent lane. Not necessary for most situations, but could, especially if we have a longer repair where we want to have some load transfer to the adjacent lane. Concrete placement with a single roller screed, going from the side here in this case. And then we'll real quickly touch on longitudinal full depth repairs, another common one. Here you can see a center line repair prepped and ready for concrete placement. This is kind of a newer detail. It's still in special provisions, but it's used a lot. MDOT does it a lot nowadays on any of their concrete repair jobs. They do have special provisions that have details for them. So here's the concrete placement going on. You can see the original longitudinal joint there where they actually had some transverse full depth repairs that were done first there, and then those come through to the middle, and then they jump over and do the next one, as you can see for concrete placement. Real quickly on items used, these are just a sampling of what we typically might see, or some of those you might see on a concrete repair job. Most of them in the 603 portion of the spec book, except for long repairs greater than 100-foot long. Those fall under the 602 part of the spec book. So assuming a 9-inch, for example, this would be the item number for 9 inches, as well as the repair number for 9 inches being that 603 number. I just picked 9 inches as an example. And then the longitudinal full depth repairs have special items still being in special provision that have that underscore and then the 7 in the middle of that item number. Where would those show up on a job? Here's an example. I'm not going to get into the specifics of all of them, but again, pavement repair could be a scoping, and pavement repair and scoping, sorry, could be a whole nother talk in and of itself, and we're running out of time. So I'd be happy to talk about that in the future and answer some questions here. But just quickly to summarize before we get into some questions, we're here to help. We understand, those of you obviously on the call are probably interested in concrete. Thank you for that interest. Please let us know how we can help. That's our job as the industry trade association, is to make sure that you have all your questions answered about concrete. And if you do choose to use it, we want you to do it right so you're happy with the end result. It's not rocket science, and it's not hard long term. What do we do with it? If we make this choice to use concrete, how do we repair it, etc. I hope I gave you an idea that it's not too difficult, but that's our job. We're here to help. I'm one of 6 technical staff that we have at the association. And we have a number of members that are experts in this that we can draw from as well if we have questions that we can't answer. But we have 2 more upcoming webinars. We'd love to see you on those, and I'd be happy to schedule some more and answer any questions at this point.
Yes. So let me put just one more time here. I'll put the info into the chat for the survey. Please take that. If you have to go, like I said, we're going to keep recording. We'll record some of the answers for the questions and everything. All right, let's get into a few of these questions. So earlier on, I think you had said that there's no real benefit in greater than having 6 inches of aggregate base. That's really for your residential streets, your collectors. If you've got more traffic, heavier loads, in that case, maybe you use a little bit more. Yeah.
I have seen some 8-inch ag bases. Yes. On some heavy duty industrial type of sections. Yes. Where they would bring in maybe 12 inches of sand sub base, especially if it's not a good subgrade. They bring in that, and then they bring in 8 inches of ag base and compact that appropriately, and then build a pavement section on top of that. I have seen that. And then MDOT does, in the metro region, they'll do 16 inches of open graded drainage course. Otherwise, they'll do 10 inches of sand and 6 inches of open graded drainage course. They do some where they'll do stabilized bases, cement treated bases as well. So yeah, in general, that results in a better performing pavement, but in most lighter traffic situations is not warranted.
Yeah, you're not going to see the cost. The cost does not give you the benefit that you might with a different type of application. All right, so some of our other questions here. There was a question about putting HMA on top of a concrete, and would you have the same joint method? So, some other folks kind of answered that for you in the chat, that maybe not be the most recommended option to put HMA on top of concrete, because you can get those reflection joints through. Is there anything that you would recommend if somebody is in that position and that is what they're being asked to do?
Yep, we see it done all the time with old concrete roads that have been overlaid, whether it's the widening or concrete base repairs that they don't want to do detail 7s and 8s. They'd rather do a concrete repair because it's that far gone. We've seen it where they'll go in and do concrete repairs to the surface and then come through and mill the concrete and the asphalt off and do a new asphalt overlay. So yes, we see it all the time. We see some agencies elsewhere in the country do composite pavements from the start. And in fact, the reconstruct of I-80 in Pennsylvania, I just heard from our counterparts over there, Ohio state line to the east, 5 miles, just is going to get started this summer and next. And they are going to be doing total reconstruct, but then they're going to do concrete base with new asphalt on the new concrete. So it is done elsewhere. And then for whether it's widening or concrete base repairs or other reasons, in that case, the only real thing is for the jointing, no, we would still joint it. And it would match the existing joints adjacent, especially on widenings and things like that. And then we would use a clear curing compound instead of the white, because the clear curing compound does not have the white wax in it. And so it doesn't act as a debonding for the new asphalt. And then the tack coat can actually stick to that concrete. So that's the other difference in if you're going to overlay it right away.
Perfect. All right, this is a great question too. Talking about sidewalks and some of the ADA considerations that, like, a quarter to a half-inch difference between your slabs is a concern for folks. And so they're wondering if there's anything. So this person said, currently aggregate interlock is the only thing that's trying to keep adjacent slabs from moving differentially up and down. Is there anything, different joint details or concrete or sub-base thicknesses, sub-base materials, other strategies that they could use to try and prevent that differential displacement of those sidewalk slabs?
Yep. And that, historically, maybe wire mesh did do that and overcame some of that, where you have tree roots growing under and pushing one slab up and things like that. But yeah, it does happen in sidewalks in urban situations, trees, etc., and utility cuts or whatever it is. So I'm not advocating for wire mesh, so let me back that up. But I would say probably fiber reinforcement if you're going to do anything, whether you do the 1.5 to 3 pounds of micro synthetic or fibrillated polypropylene, the old school fiber reinforcement. The newer ones that have come around in the last 10 years are the macro synthetic. They're bigger, thicker, actual pieces of plastic fibers. Okay. They're more substantial. They're not little wispy 1 pound test fishing line. They're more like hairpin size pieces of plastic in there. They use more by weight in pounds per cubic yard as far as dosage rates in the concrete, typically 4 pounds per cubic yard, plus or minus maybe 4 to 5 pounds of that. And those, either way, I would recommend fiber reinforced concrete mixture be used if that's
all right. And that's, a preventative thing. If you've got sidewalks that have moved, but they're stable, like they've kind of stopped moving, you can, one of our folks, Jane suggested, horizontal cutting. You can mill those down if they have kind of stopped moving and they've now found their home.
Yes.
That can be a.
Yep. We've seen that they'll go out with various different grinders or surface, equipment that they can chop that lip off. Yes. Anything 1/4 inch and below is okay. ADA wise, anything from a 1/4 inch to a 1/2 inch has to be remediated. Anything over a 1/2 inch has to actually be a ramp, as far as you can't, whatever you put back or grind to has to be, meet ADA. So understood that's a concern, but that's probably the cheaper option. The fibers being, if you're going to do it from the new replacement, that's.
All right. So this person said they've seen an increase in scaling since new limestone cement requirements have gone into effect. Does MCA recommend, what does MCA recommend to protect against scaling, assuming that placement was performed correctly?
Yes. That's the big assumption. Where we're finding where scaling has occurred, placement and finishing has not been performed correctly. That's the main reason. So, but assuming it is, you can protect the concrete with a sealer. And if it's late in the season, fall placements, you could use a cure and seal. If it's early enough in the season, you can come back before the cold weather comes, after the curing compound has worn off, because that wax-based curing compound will prevent the sealer from actually penetrating. So you can come back in with a penetrating sealer, silane or siloxane sealer is what we recommend to protect it against scaling. But the even better way is to proper mix designs where they don't add extra water. They properly finish the concrete. And then the biggest thing we see is they're not curing the concrete properly. And in roughly 80% of the situations where we see scaling, it's because there's unhydrated cement particles at the surface that did not have adequate water. And because the surface of the concrete dried out prematurely, which means that they did not seal the water in that was already in there. That's the main thing is curing. So.
All right. I got a question. A contractor wants to substitute number 5 bars for CRG, so those doubled transverse joints that you were talking about. Is that advisable?
No. So regular rebar has deformations that allow the concrete to grip onto it and stay in place, right? It ties the concrete together. CRG joints have smooth bars that allow, and we need that because transverse joints open and close. They open up in the winter when the concrete contracts temperature wise, and they'll close up in the summer. We need the concrete to be allowed to slide over top of that, around that dowel bar. There needs to be a smooth dowel. That's historically MDOT would do a CRG joint on one side of the patch and a TRG. That's essentially what you're talking about is a tied joint TRG. CRG stands for contraction. We've gone away from that, and the diameter of a number 5 bar, 5/8 of an inch, works great for tie bars, but not for repeated loads going across a transverse joint. They're fine in a longitudinal joint where loads are near but not crossing. We need much more steel. We need a 1 to 1.5 inch, depending on the thickness of the pavement diameter, smooth dowel bar. Every 10 of them going across that 12-foot lane width to accomplish that load transfer. They need to be 18 inches long. A number 5 bar is not enough steel to give us that load transfer on a smooth cut in that joint area.
All right. Here's one that I expected somebody to ask. Can you talk a little bit about the effects of road salt on concrete pavements?
Yes. Okay. So road salt is necessary, obviously, for safety. Research at Michigan Tech conducted for a bunch of DOTs when Dr. Larry Sutter was still there, determined that sodium chloride is not reactive with cement paste, regular plain rock salt. However, his research concluded that magnesium chloride and potassium chloride and potassium acetate and anything other than regular NaCl is reactive with concrete and can reduce it's reactive. I'm not going to get into the science of the calcium hydroxide depletion and the calcium oxychloride formations and blah 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 blah. Dr. Sutter is a very smart guy and determined all of that. So we recommend, as an industry, if you're going to use deicers, please only use regular plain rock salt. Don't use the purple stuff. Don't use the blue stuff. Don't use the little white round balls. Don't use, softener salt. Don't use, sugar beet, residue. All these other things for the concrete. If you're concerned about the concrete, does that stuff work better than regular rock salt on ice and snow? Yes. So that's number 1. Number 2, don't pre-salt before a storm if the storm has a lower chance of actually happening, because especially with brines, especially with magnesium chloride and calcium chloride and other brines, especially on your concrete, it soaks in, and then if the storm never comes, it never gets diluted and it just stays there. So and actually salts are hygroscopic, whatever it is. They attract moisture. And again, I'm not a chemical guy, I'm a civil guy. So they love water. They grab water and they hold on to water and they keep the concrete wet. All salts do, even sodium chloride. And so not only do they cause a thaw to occur when they're applied and then it refreezes, or increasing the number of freeze-thaw cycles, the bad salts will actually react with the concrete. The salt itself can attack, new concrete as well. We recommend if you're doing late fall placements, again, use a cure and seal to try to seal the concrete because it doesn't have a lot of time to get nice and impermeable prior to that first salting and that first few freeze thaws. So, yeah, use as little as possible. Only use it when you have to. We have a concrete parking lot at our Lansing Training Center. And it was built in, I think, 2007. It looks very much like it did within the first year after it was done. We never salt it, and we just have them plow it. We do hand salt on the sidewalks, but the actual lot itself where the cars are, we never salt. We push the snow, and we generally don't have an ice problem. So I understand liability, and we have to, and safe roads and all of that. I just, whenever I can, I try to encourage people, less is more.
Yes, yes, I think that that is a good statement across any type of winter maintenance. All right, let's see. Kind of a more general question. What do you see as some major advancements that are happening or innovations that are happening in the concrete world? This person, should we be focusing on new cementitious materials or fibers or admixtures? Is
Yep.
it more on the design, construction approaches for durability, for sustainability, reducing thickness, all that stuff? And do you have any examples of any recent efforts or recent success stories?
Yes. Up until the current administration, there's a lot of push for low carbon concrete mixes. And so that research is still going to keep going. There's less of a top-down approach to it. It's still the right thing to do, and other owners and folks are still pushing it, and it also results in better concrete in most situations. So lower carbon, meaning cements that don't chemically have to drive off carbon dioxide in order to have calcination of the limestone. If we had 100% green energy, we'd still have cement production give off carbon dioxide because you have to drive off CO2 from CaCO3 limestone in order to have CaO, the lime, which is the active ingredient in cement with all the other things, the silicates and the aluminates and all the other stuff. So again, I'm not a chemical guy, but I know just enough as a civil guy. So a lot of low carbon research on different cementitious materials. MDOT has actually been very low carbon with their concretes, especially in paving concretes, for a long time. They have done optimized concrete mixtures. I showed that slide earlier with the orange balls that kind of denoted aggregate sizes and how much you can pack into a given space. They've been doing that for over 15 years on every single yard of paving concrete, pretty much that they do. So they have some of the lowest cementitious content mixtures of any state that does concrete paving. So where we can do as low as most mixes are, we allow as low as 470 pounds per yard, which is a 5-sack overall, and up to 40% of that is slag cement. So very, very low amounts of actual Portland cement already being used. And then if that Portland cement is lower carbon, or even better. So yeah, that's where a lot of the research has been done. There's always research into different chemicals and construction techniques, and I don't know much about 3D printing, but there's a lot of talk about 3D printing with concrete. I don't know anything about it yet. There's a lot of folks getting into it. It's still very, very new, but there's still a lot of research and technology being developed.
Yes. All right, here's a QA/QC question. So this person says, in the QA/QC world, longitudinal joint repair is a major headache because epoxies today have a difficult time holding dowels in at the required spec. Is this something that you guys are talking to maybe ACI or MDOT about?
No, but I'm making a note to start asking some questions.
Okay, all right. And then continuing on with the rebar type of questions, what are your thoughts on using basalt rebar instead of coated steel?
Ooh, yes, I do like that stuff. The non-metallic rebar. ACI came out with their 440 guide. And so there's design guidance to the engineers on how to use these non-metallic fiber rebars with that have the epoxies or other resins, I guess, as the filler along with those depending on this particular one, basalt, there are others out there. And yeah, it's amazing. Zero corrosion, lighter weight, love it. They don't bend. Obviously, you can't field bend the bars, but they can account for that by having pre-bent shapes. That not that most times stuff is done back in the shop anyways. Not at the rebar manufacturing shop, but a lot of times at the fabricator will bend everything. They'll usually buy straight stock. But so that little bit of change as far as where that occurs, as far as buying different shapes. But for straight and other applications, I love that stuff. Yes.
Awesome. All right, here's a question about mastic. Can you talk about utilizing mastic for minor spall repairs? MDOT has a special provision for mastic repairs. However, this person is trying to propose utilizing the same color in lieu of black for the smaller repairs, small spalls, but it's really costly. Do you have any thoughts?
Yeah, the gray stuff, MDOT has done a few projects with it where they contracted it out. Techcrete or Flexcrete, I don't know, a couple different ones out there that have the gray mastic type of material. And it is more expensive than the regular black asphalt looking stuff. So I do understand that. And manufacturers are always trying to produce, different materials that are easier or work better. And for the maintenance crews out there that are tasked with doing that, or repair crews on a contract basis. The black mastic stuff I don't love. Not only does it show, it highlights and it's fairly wide. It does work. I do see that. It's longer lasting than cold patch. It does a better job than just black hot pour rubber like joint seal or crack seal will do. I still don't love how wide it gets and how it can create bumps, and especially when used in a wide band, like 6-8 inches wide. I've seen at times is fairly noisy in certain situations if it gets sticky in the summer and things like that. So I think some of that stuff is overused. The AMZ, spray patcher, especially at joints where then if they come and do repairs in the spring or the fall when some of those joints might be a little bit wider and you actually put compressible material in the joint when it's opened up a little bit. And then in the summer, it's actually causing some blowups and some other future failures, compression failures, bigger spalls, amounts of cracking, things like that we've seen because of that maintenance practice. So I'd rather see nothing done and then, contract a crew to come out and blow out cracks and joints or do, repairs, put, expansion joints in if they're needed or what. I understand it's reactive and quick and safer because they're in a vehicle or behind a piece of machine or whatever. There are reasons, there are benefits to why it's good, but I used sparingly in limited amounts. I'm okay with it.
All right, I think that gets us to all of our questions. If I missed yours, I apologize. I think that's everything. If you have another one, go for it. I know we went a little long. I apologize. If you've got it run, let me just put the survey stuff in here one last time. Please fill that out and let us know what other types of topics you might want Steve to talk about or some of his coworkers to talk about. We're going to have them back for those second and third sessions later on here in the spring. Thank you guys for all coming. If you've grabbed the survey link and you've completed it and you wanted your certificate of attendance, you've completed that survey, you're free to go. Thanks again for attending. If you're having any issues using that survey, let me know and I will try and help you out. Thanks again. Like I said, this is recorded. I'm going to stop recording now, but I'll hang out for a little bit. Steve, thank you so much. This was awesome.
Thanks, everyone.
Great feedback so far. People are very grateful for the content and thank you again for attending and for presenting today.
Yep, you bet. Appreciate it. Take care, everyone.